last speaker of this track is Eric Neuman from Unaffiliated.
Yes.
Great. And he's going to talk about the roadmap to a sentence stack. So,
Thank you. So yeah, roadmap to a sentient stack. So first of all, whoa, can you guys hear me? First of all, I want to take this moment to introduce myself since I am unaffiliated and because this is sort of a little bit of a different kind of a talk than you guys have probably seen most of today. So my name is Eric Neuman. I'm the CTO and VP of products at a startup company called Decision Desk. We are a Python-based shop. We have, as of yet, not dipped into machine learning, but that may eventually change. We are always looking for smart Python people. If you guys are interested, contact me after. But that is not what I'm here to talk about tonight, really at all. So moving on, I have been a lifelong fascinated person with AI. I've worked on a couple of AI projects. Thanks. I've worked on a couple of AI projects in my professional career. I worked on some stuff at NASA that had to do with aircraft that fly themselves. I focused on it in college. I wrote some AIs for some sort of hobbyist Xbox 360 games that were pretty good at kicking people's butts at flying spaceships around. And I've done some work with spam filtering as well, but mostly just sort of tinkering in my garage kind of stuff. So again, this talk that I'm about to give to you guys is a little bit different than the ones that you guys have heard already. Primarily, this is going to be a talk about theory, a little bit based on observation of trends in the AI space itself, and also largely in the way that projects can expand from being little pocket niche projects into being things that really grow to encapsulate the whole world and become world-changing things. So with that said, let's just go right into it. So setting this up, I think that AI today is in sort of a similar state that computer science was about a century ago. Now, what I mean when I say that is that right now, each AI that exists, each program is a single-purpose entity. For the most part, we have these pieces of code that are out there that do one thing and one thing only. We have a piece of code that filters our spam out. We have a piece of code that kicks our butt at video games. We have a piece of code that might recommend what kind of stock we should buy or sell. But each one of these things does those things and those things only. Well, this is very similar to machines and computers that we had about 100 years ago. This beautiful looking thing is an adding machine, and it represented the state of the art about a century ago. It, along with all of its brethren machines, were individual computers that only were capable of doing one single thing. And they did them beautifully. And I want to really take this moment to say that I am in no way disparaging the work that has been done in AI. I am absolutely flabbergasted with some of the things that I've seen today. They are truly works of art. Some of the things that I've seen today especially have really just blown me away. But there are some negatives associated with doing work in this manner. First and foremost, it's unapproachable. In order to build something like this or work on a program like the programs that we've seen today, you need a really, really, really large amount of information and domain knowledge about artificial intelligence, about programming, about open source software, about all of these different things. And each one of those things is a barrier to entry. It's very similar to the kind of barriers to entry there were on working on computers 100 years ago. In order to work on something like this, you had to be a mechanical engineer, you had to be a computer scientist, you had to be a mathematician, you had to be all of these things. And it wasn't until those barriers were really blown away that computers became the general purpose, world-changing devices that we know and love. So how did this change? Well, somebody came around and proposed an idea for a theoretical machine that is one level of meta up from that adding machine that we were talking about before. Of course, I'm talking about Alan Turing. Well, I am humbly attempting to follow sort of in that direction. I think that we need to take one level of meta up from where AI is right now in order to take it to its true world-changing potential. So I take it everybody knows what a Turing machine is here in this room? Okay. So I really want to stress that I'm proposing a sketch of an idea of a direction that I think that we could go that would take us to a future that I think probably everybody in this room is interested in. A future where mankind is capable of producing really a new friend, a kind of a new type of mind that exists solely within computers. And I've also want to note that the pictures in this presentation are sketches on purpose to back that thinking. Okay, so with that in mind, how could we even conceptually do something like that? Well, in order to start talking about that, I want to discuss what I call the highest level pseudocode ever. So earlier today in one of the talks about hyper-optimization, this was also discussed. There is a process that AI programmers go through when they sit down to write an AI, and it's very similar. It pretty much always goes like this. Observe a problem, model the problem, select the algorithm that has a good history with similar problems, apply the algorithm to the problem, run the pair. If results are good, you win. If results are bad, adjust parameters. Eventually, you may have to abandon the algorithm and try a different algorithm. And ultimately, if you really can't find an algorithm that works for you, you may abandon AI entirely in favor of brute force, or even further, God forbid, in favor of a human solution. Now, I don't know about you guys, but to me, this sounds like a highly scriptable process. If we can conceptualize a way to get all of the information and all of the bits and pieces together in a way that machines can actually operate on it. Well, that's what I want to really talk to you guys about tonight and convince you that that is something that's approachable and possibly attainable with today's technology. So that thing I've been calling the do anything machine. I realize that that name is possibly completely ridiculous. It's somewhat intentional. You know, one of the things that I think AI really suffers from is this level of unapproachability and this level of such extreme technicality. I mean, the talks that we've seen so far today, although mind-blowing, are also mind-blowing. They're designed to be conceptualized and discussed by people in this room and not by the rest of the world. So I've tried to keep my thoughts and my discussions about these things in the types of terms that are approachable to almost anybody. So here we go. Do anything machine requires a generic problem statement class. This is by far the most difficult thing I have ever worked on in my life. Trying to come up with some kind of a class that could contain the entire sum of all the world's problems that you could inherit from to, say, design a to have a problem that is, how do you build this bridge? Or have a problem that is, how do you optimize stock trading? Or have any of the things that we've talked about today, along with all the other things that are existing in the whole world. Extremely, extremely complicated. But if we could accomplish that, the next one is slightly less complicated. Problem comparison algorithm. Again, this is going to be something that we need. It's pretty difficult, but I think that there's some things available to us today that will allow us to really cheat this and do it with off-the-shelf technology that's available and readily usable to everybody. The next thing is a unified collection of algorithms. This, I think, seems like the most overwhelming piece, but is actually the piece that has had the most work done on it. There's a lot of packages, some that we've seen at this conference, that are already working on this. A collection of AI algorithms that follow the same form so that you can easily adapt your problem to it over and over again, to each of these different ones without having to waste that work. These projects are going in the right direction. To name a non-Python project that I've worked with, Weka, I think is really cool and does a pretty good job of this. The next thing, obviously, we're going to need storage. And lastly, we're going to need lots and lots of CPU time. Okay, so this is just one possible way to build a do-anything machine. This is the one that I favor and I have thought about the most. Basically, the way that it works is the first time you run it, it's going to try all possible configurations of all possible algorithms. The reason why we need to do this is we need to start out by building a base of knowledge and understanding of which algorithms are good at which problems. Certain types of AI algorithms are very well matched for certain types of problems. For example, the traveling salesman problem can be solved by genetic algorithms in just under 100 cycles, whereas the traveling salesman problem takes about 1,000 cycles if you're trying to solve it with neural nets. That represents a tremendous waste of work. If we were talking about a much more sizable real-world problem, like the designing of a bridge, the wasted work by using the incorrect algorithm could be astronomical. In fact, it could be such a combinatorial explosion and such an enormous amount of work that we're wasting that it might make it completely unapproachable, causing us to do that thing where we fall back on a brute force or human solution. The next time we run the do anything machine, it's got to do the same thing. It's got to try every different possible combination of configurations and algorithms. The third time that we do it, magic can sort of start to happen. if we do things right. It can compare the previous two problems, and it can start with the best configuration for the most similar problem. What this means is, if all these things that I've just discussed are possible, every time we ask the Do Anything Machine a question, it gets better. It gets better at matching algorithms to problems, and it gets better at pruning off that work that is otherwise being wasted. I think that this represents, or could represent, a significant step forward. Now, some people have already been working on this stuff. Again, something we've heard about today, but I still think that this is a worthwhile goal because of the things that I'm about to talk about. Okay, so let's look at some code. Now, I have admittedly got very, very little code. I had intended to have a proof of concept that just demonstrated very simply 3 or 4 problems that it is able to zero in on a more accurate one, but I had a severe case of real life getting in the way over the last 2 months, so I really just have some stubs of code. So let's just very, very briefly gloss over what I've got here. So I've got a base class, which is the question class. I've decided to go with a model of a paradigm of space exploration and question asking in my particular implementation of this Do Anything Machine. First thing that you'll notice here is I'm very careful to document everything. This is going to be really important later on, and it's also going to be important right now. So I was mentioning before that I think there's some things we can do right off the shelf to do problem comparison cheaply today. One of those things is we can cheat. We don't actually have to compare problems. We can simply require human beings to input textual descriptions of their problems and rely somewhat on textual analysis and textual similarity to compare problems right away. In order for this thing to start, to get off the ground, we just have to have a barely working problem comparer. It has to only be slightly better than random chance in order for this thing to work theoretically. The next thing we have here is the check function. So the purpose of the question object is to serve as an interface between the Do Anything Machine and its corresponding packages and all the other packages that are required. The idea is we've got this thing here, model, which I don't think I'm going to have the time to dig into today, but basically the idea behind the model is it's a series of simple classes that allow people to inherit from them and create objects which will be ultimately serializable down to a format which the Do Anything Machine can deal with. A unified format that is data agnostic, that's really model agnostic. This is a place where I could really use some NumPy, and if I had known about it 3 months ago, would already be using it. The point is that the check algorithm here is a place where, depending on the problem that we're doing, we can loop in a fitness checker that involves any kind of other software. In the example of trying to build a bridge, we might loop in a physics modeling problem, which would take our coordinate object, which essentially represents one space or one possible solution in a space, convert it back into a model that the physics simulator can use, evaluate it on some basis, return to fitness, and turn it back over to the seeker class. Yeah, sorry, unfortunately, I don't really have enough time to dig into this more. If you guys want to talk implementation, I'm more than happy to talk after, but really I'm trying to get across the ideas of the stack today. So implementation is going to take a backseat. Okay, the Sentience Stack. If you guys can swallow all the stuff that I just put out there, which believe me, I understand is a lot, we can start to talk about some really, really fun, very, very futuristic stuff that may be attainable in the near future. Do Anything Machine, defined as a thing that can solve any solvable problem given enough resources. That's what we were just talking about. If such a thing is possible to be constructed, we can create one of my favorite things, which is called the self-improvement engine. Uses the Do Anything Machine to improve the components of the stack itself. So as I was saying before, the problem comparison algorithm only needs to barely work in order for us to get this thing off the ground. If we can get it to barely work, as we gather up data, as we ask it more and more questions, it becomes more and more reasonable to ask the Do Anything Machine itself, how can we design a better problem comparison algorithm? There's a lot of different ways this could be done. I mean, my personal favorite way is through code evolution. When you have lots and lots of CPUs that are cheap that we have today, it becomes actually pretty reasonable to start doing sort of this type of thing. Next layer is the networked layer. Can ask for help from or assist other stacks or just compare notes. The idea behind this, and my favorite example, is if you imagine a Do Anything Machine in my hometown, in Brooklyn, that's being used by some plumber. And this plumber is using it to help him design the plumbing systems for tall buildings. That problem is fairly similar to the problem that a farmer in Africa is experiencing, asking his do-anything machine to design irrigation systems for his farm. Those two do-anything machines should be talking so that the farmer's do-anything machine can avoid having to do all the extra comparison, all the extra work that the one in New York has already done. Those problems are similar enough that starting with the same approach, the same combination of algorithms and parameters, should theoretically allow it to cut off some of that work, to prune out some of essentially what amounts to extra monetary expenditure. The creativity jiggler is probably the silliest piece of this potential stack, and the one that is going to make the least sense to the people in this room. I think this one is most strongly influenced by my background in cognitive science and in psychology, and in my observations of creative people that I've interacted with in my actual life. People who are good at solving problems tend to know intuitively when to crumple up what they're working on, throw it away. That is something that our machines don't do almost at all right now. There's some work that's gone into this, in terms of simulated annealing and hill climbing and things like that, but being able to apply that kind of thinking across this stack is a whole area of study unto itself, which I have not dedicated nearly enough time to. But I'm convinced that it would be incredibly important for this thing to even aspire to be what I'm intending it for it to be, which is essentially a baby mind. The next thing is the problem recognizer. The problem recognizer sorts through data to figure out what needs to be figured out. So, sounds really weird, really, really important. If you imagine a do-anything machine loaded up inside an actual robot that has hands and eyes, you put that robot in a room with a door. It's not going to have any reason or any way of figuring out how to open that door. Not because it can't figure it out, but because it doesn't realize that it needs to figure that out. Do-anything machine needs some way to convert information around it into problems that can be solved by itself. That's the purpose of the problem recognizer. So essentially take a random amount of, or not a random, but a large amount of data that's being fed in and determine where there are problems that could be evaluated, and then probably ultimately decide whether or not to act on those. Which brings us to the next thing, the motivation complex. This is by far the most interesting piece, and the piece which I unfortunately have not enough time to talk about. I cover it pretty in depth in a paper, which I'll flash up the URL for at the end here. But the idea is essentially that the Sentience Stack is going to start out its life living in the cloud. And I think that we can aspire to a sort of a personality, a sort of a selfness, by taking a combination of expert systems that are based on resource management and action decisions, and by continuously asking a series of questions to the do-anything machine about how to balance out the decisions being made by several rigorously defined expert systems, we can zero in on something which may eventually represent or resemble a person, a thing that has its own intent. I really wish I could talk more about this, but I just don't have enough time. The last piece is called the language learner, and it uses all the other layers of the stack to learn how to communicate. Again, the idea is basically the same. Language learning is by definition a finite problem. Otherwise, people wouldn't be able to do it. If it is a finite problem, it should be theoretically possible to convert that into a question, feed it into this machine, give it enough resources, and over time expect it to begin to be able to communicate, which I think, if we are able to accomplish all these other pieces, will be what it wants. Because it will at that point be a machine mind which has no way to communicate with the world around it. Okay, super quickly. Things that I'm actually working on actively in my project. The generic problem statement. How can we possibly include other types of machine learning? Right now, I'm only capable of handling supervised learning. It seems like a reasonable enough starting place. There's all these other kinds. Problem comparison. How can we do it right now? There's pieces of software out there that exist that do looping analysis, which can return similarity between pieces of code. There's also a thing which I'm really interested called, I don't know how to say it, CyC, which is a database of semantic knowledge about actual English or human languages, AKA like A dog has 4 legs. A leg has a knee, etc., but for the entire language. Logistics. This is one of the most difficult problems to solve. How should we even store our code to best facilitate future self-improvements? Should we stash it in some sort of like a file-based system? Should we have our do-anything machines committing code online? I think that's kind of cool. Should we be pickling it and storing it in a database? I just don't know. There's too much for me to think about. Parallelization. Not even going to touch that right now. Okay, the point is, why am I saying this to you guys right here, right now? Well, basically, this project is so enormous, and I think so important, and so dependent on the open source community that I have no choice but to call out to others to help me work on it. I would really like it if people would sort of just be interested in it and start having this conversation. You know, there's a lot of barriers to even this kind of discussion inside the world of AI due to everybody's favorite Gartner hype cycle. Even saying AI is disparaged now. This is the machine learning track because I think AI is sort of a poisonous word. I would like to, if nothing else, use this as a conduit for trying to change that and get rid of the essentially prejudice against these kinds of ideas. If you're interested, the paper that I wrote is much more detailed. Simpleactually.tumblr.com is the most recent post. You can check out my repository, which is just absolutely in its infancy. Neuman, or github.com/Neuman do anything machine. And of course, that's my Twitter.
Questions for our speakers?
Yeah, two things. The first one's more of a comment, the second one's a question. Is it a do anything machine or do anything? But an actual question. Creativity jiggler and the problem recognized somewhat could be two sides of the same coin. But do you think creativity is computable?
Well, I mean, I think by definition, it would have to be, because you don't have an infinite number of neurons in your brain. So somewhere in there, there's a finite structure which is capable of producing the creativity that you are.
Okay, I mean, that's definitely one way to view it. Do you think it's computable with our current paradigm model of computing?
Well, I don't necessarily think that I know how to do it. My hope is that this structure, this sort of path that I've, suggested, is the type of thing that we would be able to build a really, really simple thing and feed it the right kinds of questions and the right kind of resources and help to guide it while it guides our actual development. Another reason why the open source is so important and not being tied to a timeline is also, really relevant.
I in a sense think you're trying to take offense, bite off a problem that's way too hard. A lot of smart people are trying to basically, AI is a very hard problem,
Mm-hmm.
and I think we have to be able to simulate the human brain with some big computer, 5-10 years from now,
Mm-hmm.
to be able to simulate human experience, right? Build a machine connected to sensors. I think this is a very hard problem, and so I'm skeptical that it can be.
You have absolutely every right to be skeptical. I'm even a little bit skeptical, and I've been working on this for years. To just comment on what you were talking about the human brain, my gut tells me that that's the wrong approach. If you look at human history of technological advances that have been really quantum leaps for us, they rarely are identical to the natural inspiration. The little blurb on my talk said, right, or like a cheetah and a race car don't look the same, but the race car works really, really well. I think that this represents a more machine-like model of a mind as opposed to a machine emulation of a human brain, which, like you said, is years away from our capabilities.
When we take an approach, we have to do something rigorous with math and have things well defined. When you define things well, in a well-defined problem, very often you limit the scope of that problem. So,
I mean, the only way we'll know is if we try.
Well, I would find it easier to buy into this. I don't think this is a road to sentience.
Is that a question?
That's a comment.
Okay.
I was just gonna ask, because nowhere in the stack was there how this would get domain knowledge? Or is it kind of a presumption that domain knowledge is just some algorithm that kind of learns the domain? Because a lot of these things, you know, depending on how you would use these solvers, you would have to kind of understand, you know, plumbing or, you know, aircraft, or you'd have to have an understanding of domain knowledge in order to solve a problem, right?
Mhm.
Or,
So the thinking that I have on this is that in the beginning, you're totally right. And that's why initially the only way to use the do anything machine is to be a programmer, right? The sort of the first goalpost is to try and create something that reduces the barriers for us to feed questions into this thing. And we would be feeding it these questions which contain the domain knowledge, right? You would be making assumptions about what you want that bridge to look like and how you want that fitness to be evaluated. But as it builds up this library of questions that have been asked to it in the past, and hopefully as we get further and further along and have more and more of those components looking inward, it should be able, maybe, to start to deduce domain knowledge from things that it's seen before. And one of my things that I strongly hope for is that library Psych, or that tool Psych. If you haven't checked it out, you should. It's really cool. Might be a really interesting way to try and bridge the gaps between repositories of knowledge like Wikipedia and the kind of knowledge that we would have sort of siloed inside the question memory that a do anything machine would have.
We're going to be running into the lightning talk, so I think probably best to come up and talk to the speaker, and thanks again, Eric.
Thank you.